Welcome to the videos of the power electronics converters. In this video, we will be learning the Fourier series analysis of the output voltage of a three-phase half-wave rectifier. The output voltage of the three-phase rectifier is denoted by V0 theta that you can see over here. To how we get this value or this waveform, we can understand from these waveforms of the supply voltage. The supply voltages are three-phase displaced from each other by an angle of 120. The R phase is Vm sin omega t, which is starting from 0 degree, whereas the Y phase is starting from 120 degree, and the B phase is starting again from lag by Y by 120, lag from R by 240 degrees. Waveform would look like this. Now, in this half-bridge, half-wave rectifier, three-phase half-wave rectifier, the supply voltage is connected to the diodes, single diode. The R phase is connected to the diode, and in this pattern it is connected, and it is connected to the R load, the resistive load. Now, if three supply is given to the diodes in parallel, obviously the diode which is more forward biased will conduct. If we see the waveform of RYB, this waveform of R, Y and B, at any particular instant of time, we find one of the phase voltage is maximum. From the reason from here, the R phase is maximum. Again, this point is pi by 6, that is 30 degree. So from 30 degree to 150 degree, R phase is maximum. Similarly, it is Y phase is maximum for another 120 degree, and B phase is maximum for another 120 degree. So if we copy this upper layer of these waveforms of R, Y and B, we will get the output voltage waveform in this pattern. It is very important to know what will be the cosine and the sine component of this waveform, number one. Number two, what is the average voltage? Because this voltage is unidirectional DC. It has got an average value. We will determine what is the average value of this output voltage. Apart from that, we will also find its cosine and sine term. Now, we can see this from the figure. It is clearly that it is not like, it cannot be said of f of theta is equal to f minus of f theta. Sorry, f of theta is not equal to f of minus theta. That means the waveform from this x-axis to the right is not the same as from the x-axis to the left, if looking at this waveform. So that we cannot say this is an even function. To make it an even function, we can draw this output voltage waveform in this pattern with the y-axis here. Now f of theta will be equals to f of minus theta. The advantage of making this an even function is the Bn term in the Fourier series is eliminated. Now the output voltage can be, let us say this is V0 dash theta. Now output voltage can be said as VDC plus summation of n from 1 to infinity an cos n theta. Now we simply have to evaluate the value of an and the average value. And shifting the y-axis will not make any difference apart from adding a value at the end as a phase lead. So let us first take this waveform and evaluate the output voltage. DC voltage, that is the VDC, is 1 by 2 pi 0 to 2 pi V0 theta d theta. Now we are taking the interval, 1/3 of the interval. So we divide the entire 360 degree in 1/3 of it, that is 120 degree. So we can write 1 by 120 degree is 2 pi by 3. Integrating from minus pi by 6 to pi by 6, this is a cosine waveform, so Vm cos theta d theta. After evaluating, we get 3√3 Vm by 2 pi. After that, we will evaluate the An term. When we evaluate the An, we simply have to, An is 1 by pi 0 to 2 pi V0 theta cos n theta d theta. So we can see from the average value what is the An is 1 by pi. So simply from 1 by 2 pi by 3, you just write 1 by pi by 3. Rest of the things same with cos theta, cos n theta. And then we do the integration of it. After doing the integration, we come to the value that this is coming around 3√3 Vm by pi cos n pi by 3 by 1 minus n square. For n is equal to 3, 6, 9. Because you can see from this equation over here, the n term is here and sine of n theta is there. So if I put the value of here n pi by 3, so n, if it is 3, if it is 6, if it is 9, if it is 12, the right hand side this term will be 0. So only the term which is left out is this. That is why we take the limit for the left hand term and we get this value. Then if we put the value of VDC and AN here, so we get the values of V0 theta dash is equal to DC term average value 3√3 Vm by 2 pi plus 3√3 Vm by pi. And when we substitute the value of n here 3, this is cos pi is negative, the lower term is negative, it will be a positive term 1 by 8 cos 3 theta. When we substitute the value of n is equal to 6, so this is upper term will be positive, the lower term will be 1 minus 6 square is 35 negative. So this entire term is negative. So similarly we get 1 by 8 minus 1 by 35 plus 1 by 80 minus 1 by 164 and so on. It's like we are getting a positive, then negative, positive, then negative value. Now we can get the Fourier series expression for V0 theta. What? By just shifting the value of theta to 30 degree on the left leading. So if I say cos of 3 theta over here, we will write cos of 3 theta plus 30 degree. Now see the waveform again. This waveform we get by shifting this waveform. If we shift this waveform 30 degree left, if this waveform what we get the DC voltage waveform, so unidirectional voltage, if we shift this waveform to 30 degree left, we will get exactly this waveform. When we shift to 30 degree left, that is why we get here we add plus 30 degree to all without having any error. So we can simply put 30 degree to all and we can get this up to here. Now let us take the value of Vm is equal to 100. So if we put the 100, this average value is 82.7. And the fundamental, not fundamental, the third harmonic peak value is 20.67. And the sixth harmonic peak value is 4.72. Similarly, ninth harmonic is 2.06. And let us see the spectrum analysis of it. The DC component, if we try to normalize it, that means if the DC value we say, let us say it is 1, that means all the components, we will divide all the components by 82.7 or 0.827 in the formula. If we divide all the terms with divide everything with DC value will come out to be 1. and the peak value of the third harmonic will be 25% of the DC value. Sixth harmonic is 5.7% and the ninth harmonic is 2.5%. This is important here. The third harmonic is dominating. Our objective is, when we have a rectifier, our objective is the output should be a DC voltage. There should not be any AC waveform. But what we are getting, apart from DC, we are also getting the AC waveform, the third harmonic voltage, sixth harmonic voltage, and ninth harmonic, where the third harmonic peak value is 25% of the DC. Sixth harmonic peak value is 5.7% of the DC. These are the dominating AC waveforms, and that is dangerous because these on the output we need only perfect pure DC. So these harmonics need, these AC waveforms of third and sixth harmonic need to be filtered out. So this is the important message, and hope you have learned it and you have understood it. For any doubt, please comment. Thank you very much.